and welcome to our video on Green's functions. We have so far studied Sturm-Liouville boundary value problems of the form the differential equation looks like first derivative on the product p of x times f prime plus q of x times f equals lambda r of x times f plus a function h of x, where h may or may not be 0, plus some associated boundary conditions. And we solved the non-homogeneous problem with formal series, or eigenseries. If we compress, as usual, the differential equation part to the operator SR on f equals 1 over r of x times first derivative on the product p of x times f prime plus q of x times f, then the ODE part is equivalent to the operator equation SR minus lambda identity operator on f equals h over r, where my identity operator just is identity on f equals f. So if we're able to solve this equation at the operator theoretic level along with the boundary conditions, we're effectively inverting the operator SR minus lambda times the identity. That is, we've solved for f equals SR minus lambda times identity inverse on h divided by r. Where we're thinking of the inverse of an operator, just like you might have the inverse of a matrix. And in matrix analysis, we know that we can calculate a matrix inverse if the matrix has n linearly independent eigenvectors. We did this in the optional appendix reading, and that's one way of getting a matrix inverse. And this is a very elegant way of doing it, I think, in that you get a very clear formula, without having to go through the mechanics of numerically grinding out the matrix inverse. But it's not always possible. Not all matrices have n linearly independent eigenvectors. Even though without the nice eigentheory, we could still calculate the matrix inverse just doing it brute force. And so we might ask ourselves, can we do what we did before without using eigenseries? Can we solve boundary value problems without necessarily calculating all the eigenvalues, finding the corresponding eigenfunctions, and writing that series? To say nothing of whether or not the series actually converges. And the answer is yes, we can, if we think from a different point of view. So can we invert this operator SR minus lambda identity? What would this really mean? What are we looking for here? The operator SR minus lambda times identity maps a certain subspace D of SR, which we know is contained in the C2 twice continuously differentiable functions, back to the continuous functions. Right? SR takes two derivatives, so it'll take a twice continuously differentiable function just to a continuous function. And we work with SR on this special subspace D of SR that encodes all the boundary conditions. So we would like to find a linear operator, call it T, that goes in the reverse direction. That should go from the continuous functions on the interval a to b into our domain D of SR, such that we have the following identities. If you apply t to SR minus lambda I on a function f, you get back f, where f is any element of the domain D of SR. And if you apply SR minus lambda times the identity to t, acting on a function h, where h is a continuous function, you get back h. That is what an inverse of any map, linear or nonlinear, should do. One difference in this video and in this part of our course. Instead of focusing on the special form of the Sturm-Liouville boundary value problem, we'll work with a more general second-order operator, call it A on f, where A on f can have variable coefficients, and this differential operator A on f looks like phi of x times f double prime plus psi of x times f prime plus theta of x times f. And of course we'll require phi to be non-zero. Phi of x can never be 0 for any x. This is a much more general second-order linear differential operator like we saw earlier in the course. And what we're going to show essentially is that how this operator's inverse behaves, how A inverse on H acts, well, we can represent it as an integral. Namely, we're going to find a function g of two variables, call them x and c, such that the inverse operator A inverse on h at x is given by the integral from a to b of g of x xc times the function h of xc integrated with respect to xc. So you start out with the function h. You want to figure out what A inverse acting on h is. I claim it is this integral operator on the right, where you multiply by the special function g and then integrate. And this should feel comforting to us. A is a differential operator. A takes derivatives. What is the inverse of the derivative? The integral. So we'll end up writing the inverse of a differential operator as a special kind of integral operator. And to do that, we need a rather technical lemma. And I'm going to walk you through it in detail. So let's say that our coefficients of this operator A, phi, psi, and theta are all continuous, and phi is non-zero. And looking towards the boundary conditions, we'll have four numbers, alpha 0, alpha 1, beta 0, and beta 1, where at least one of alpha 0 and alpha 1 is non-zero, and at least one of beta 0 and beta 1 is non-zero, which is, of course, familiar to you from before. Now let's look at the boundary value problem of the form phi of x times f double prime plus psi of x times f prime plus theta of x times f equals 0 on the interval a to b, with the familiar boundary conditions alpha 0 f of a plus alpha 1 f prime of a is 0, and beta 0 f of b plus beta 1 f prime of b is 0. Suppose that the only solution to this boundary value problem is the trivial solution f equals 0. Then I claim there exist two functions, g1 and g2, that are twice continuously differentiable and that solve the following, shall I say, half boundary value problems. So what does g1 do? g1 satisfies the differential equation, phi of x g1 double prime plus psi of x g1 prime plus theta of x g1 equals 0. g1 satisfies the boundary conditions at a, alpha 0 g1 of a plus alpha 1 g1 prime of a equals 0. G1 does not satisfy the boundary conditions at b. Beta 0 g1 of b plus beta 1 g1 prime of b is not equal to 0. And g2 satisfies the counterpart half BVP, phi of x g2 double prime plus psi of x g2 prime plus theta of x g2 equals 0. G2 does not satisfy the boundary condition at a. Alpha 0 g2 of a plus alpha 1 g2 prime of a is not 0, but g2 does satisfy the boundary condition at b. Beta 0 g2 of b plus beta 1 g2 prime of b equals 0. And moreover, these two functions, g1 and g2, are linearly independent. So I claim, just to recap, if you only have the trivial solution to the original boundary value problem, then you can find functions that solve the half boundary value problems, and those functions must be linearly independent. And these functions g1 and g2 will be the building blocks of that function g of x and c, that kernel of the linear operator from the previous slide. So I'm going to walk you through the construction of how we can be assured that g1 and g2 actually exist. First, I claim we can find numbers mu0 and mu1 that are not both 0, and gamma 0 and gamma 1, another pair of numbers, also not both 0, such that alpha 0 times mu 0 plus alpha 1 times mu 1 is equal to beta 0 times gamma 0 plus beta 1 times gamma 1 equals 0. And why is that? Because I assumed at least one of alpha 0 and alpha 1 was non-zero, and at least one of beta 0 and beta 1 was non-zero. So sit down, consider the cases on alpha 0 and alpha 1, beta 0 and beta 1, scribble for a while, and you'll see that you can come up with these mu 0s, mu 1s, gamma 0s, and gamma 1s. Now, for shorthand, let me call my differential operator A. So A on f will be phi of x f double prime plus psi of x f prime plus theta of x times f. And then I'm able to solve the equation A on f equals h if and only if f double prime plus psi of x over phi of x f prime plus theta of x over phi of xf equals h of x over phi of x. Right? Easy peasy, just dividing by phi of x because I assumed that phi is never 0. So what do you see on the left? You have a continuous coefficient, second-order linear differential operator. In particular, you have the f double prime by itself. And so you're always able to solve this problem, f double prime plus psi of x over phi of xf prime plus theta of x over phi of xf equals h of x over phi of x. And so in particular, I will look at the two homogeneous initial value problems, a on g1 equals 0, with g1 of a equal to mu 0 and g1 prime of a equal to mu 1, and a on g2 equals 0, with g2 of b equals gamma 0 and g2 prime of b equals gamma 1. So I claim I can always solve these initial value problems. Why? Because a is a perfectly nice continuous coefficient second-order linear differential operator, and these values mu 0 and mu 1 I cooked up from the top of the slide, and the same for gamma 0 and gamma 1. And importantly, in the curly braces here, we have initial value problems. I'm only asking for conditions on g1 at the point A, and I'm only asking for conditions on g2 at the point B. And as long as those conditions are at the same point, regardless of where that point is in the interval, left endpoint, right endpoint, middle, you know you can always solve the initial value problem. So abstractly, I've cooked up these functions g1 and g2. Now let's compute something. Alpha 0 times g1 of a plus alpha 1 times g prime of a equals alpha 0 times mu 0 plus alpha 1 times mu 1 equals 0, because of what I forced the initial conditions on g1 to be. So I see that g1 satisfies the boundary conditions at A. And you can do the same thing for g2 to show it satisfies the boundary conditions at B. But what would happen, say, if g2 also satisfies the boundary conditions at A? Remember, we want g1 and g2 to solve the half BVPs. So we don't want g2 to solve the boundary conditions at A. Well, if you have g2 solving the boundary conditions at A, alpha 0 times g2 of A plus alpha 1 times g2 prime of A equals 0, then what do you see? You see that g2 solves the boundary value problem A on g2 equals 0, alpha 0 g2 of A plus alpha 1 g2 prime of A equals 0, and then, if I put a better space in here, beta 0 times g2 of B plus beta 1 times g2 prime of B equals 0. In other words, g2 is a solution to the full boundary value problem. But that's not allowed to happen, right? The only solution to the full boundary value problem is a trivial solution. So that would mean g2 would have to be 0. But wait, can g2 be 0? No, because g2 solves a boundary value problem where at least one, g2 solves an initial value problem where at least one of the initial conditions is non-zero. So I get a big stinking contradiction here. And the same contradiction would result if g1 were allowed to satisfy the boundary conditions at B. So just using ordinary differential equations theory and a little bit of proof by contradiction, I've been able to solve each of the half boundary value problems. Now, what about linear independence? I want g1 and g2 to be linearly independent functions. Well, let's go the root of contradiction again. Suppose g1 and g2 are linearly dependent. Then g1 and g2 have to be scalar multiples of each other. So I could have g1 of x equal to lambda times g2 of x for all x and a particular constant lambda, or the reverse, maybe I have g2 equal to lambda times g1. Let's just stick with the first case, g1 equals lambda times g2. Then let's look at the boundary conditions for g1 at B. I would have beta 0 times g1 of B plus beta 1 times g1 prime of B, a quantity that I know I want to be non-zero, equal to lambda times the sum beta 0 times g2 of B plus beta 1 times g2 prime of B equals 0. another contradiction. That's the power of proof by contradiction. We get linear independence by contradiction, and we get solving precisely the half boundary value problems from before by contradiction. So I've cooked up these two marvelous auxiliary functions, g1 and g2, that satisfy the half boundary value problems. Now we're going to go back and solve the full boundary value problem and get that integral operator representation. So we'll take functions phi, psi, and theta that are continuous. Phi of x is non-zero for all x. At least one of the numbers alpha 0 and alpha 1 is non-zero. At least one of the numbers beta 0 and beta 1 is non-zero. The only solution to our full boundary value problem is the trivial solution f equals 0. These are all the hypotheses I needed for the lemma that we just proved. And here is our answer. For any function h that is continuous on the interval a to b, the unique solution to the non-homogeneous boundary value problem, phi of x times f double prime plus psi of x times f prime plus theta of x times f equals h of x plus the boundary conditions, is the function f of x equals the integral from a to b of a certain special function g of x and c times h of c integrated with respect to c, where g is the so-called Green's function for this boundary value problem. And what is g? Let us define it. We'll take g1 and g2 to be solutions to the half homogeneous BVPs from before. So g1 satisfies the boundary conditions at a but not b. g2 satisfies the boundary conditions at b but not a. And then we define g of x and c is the following complicated piecewise function. So let's parse through g of x and c carefully. It'll be one of two things, depending on whether c is less than or equal to x, or x is less than or equal to c. And when x and c are equal, we will get the same thing. So first suppose that c is less than or equal to x. Then we'll put g of x and c is g1 of c times g2 of x divided by phi of c times the Wronskian of g1 and g2 at c. And conversely, if x is less than or equal to c, g of x and c will be g1 of x times g2 of c over phi of c times the Wronskian of g1, g2 at c. This is kind of a tricky formula, and I think it is worth memorizing. The important thing is we consider cases, c less than or equal to x, or x less than or equal to c. And the only thing that changes is whether we have an x or a c inside g1 or g2. The denominators, phi times the Wronskian, are always the same, and they're always in terms of the variable c. For c less than or equal to x, it's g1 of c, g2 of x. And for x less than or equal to c, it's g1 of x, g2 of c. So g1 of c, g2 of x for c less than or equal to x, the c's are always on the left of x. And g1 of x times g2 of c for x less than or equal to c, the x's are now on the left of c. At least that's how it sort of helps me to remember it. So how on earth do you get this representation formula for a solution to this boundary value problem? Basically, just take a deep breath and grind it out. You can rephrase the ordinary differential equation part of the boundary value problem, just as we did in the previous lemma, as f double prime of x plus psi of x over phi of x f prime plus theta of x over phi of x f equals h of x times phi of x. So call the left-hand side here b on f. B on f is a perfectly nice second-order linear differential operator with possibly variable coefficients. We know how to solve non-homogeneous problems involving b. In particular, we know that g1 and g2 are linearly independent solutions of the homogeneous problem b on f equals 0. So we can use variation of parameters to get a formula for f that would involve two arbitrary coefficients, one on g1, one on g2, and some integrals of g's and the Vronskyans against h divided by phi. And then you use the boundary conditions and some of the properties of G1 and G2 that they meet one boundary condition but not another to figure out what those coefficients have to be. And then you cram everything together into one big integral, separating things out piecewise for x less than or equal to xc or xc less than or equal to x, as on the previous slide. I'm not going to make you read the proof if you don't want to. It's in the lecture notes. I find it pretty satisfying that we can use just good old variation of parameters and that very technical lemma about G1 and G2 to go from a big variation of parameter solution just to that one compact integral operator with the Green's function. It's just very, very satisfying to read, I think.